All right, so this is actually a continuation for the previous lecture. Somehow something went wrong during recording. So I stopped short of actually find out that, there's something is missing. So this is the last thing we've done is we have this summation, and we said that D divides N and C divides N over D is equivalent to saying that C divides N and D divides N over C. So this is what we're going to do next is we're going to rewrite this as C divides N for the first summation, and then we're going to do here D divides N over C, and then we have, of course, mu of T F of C, and we can rewrite this also as C divides N F of C, and then summation D divides N over C of mu of D. All right, now we're coming to the situation where we have the summation of the Mobius, the values of Mobius function, and we have a formula for that. So let's look at that. So this here, D divides N over C of mu of D. Remember, this is equal to 1 if N over C is equal 1 and 0 if N over C bigger than 1. And this is equivalent to saying that this summation is equal 1 if C is equal N and 0 if C, the divisor, C is smaller than N. So in other words, the only term which is going to contribute a non-zero number in here is when N is equal to C. And when N equals to C, this becomes, of course, F of N. And this one, we're going to come up with 1 for it, and all other divisors, D is going to give us 0. So at the very end, so we get this is F of N. And this is exactly what we, actually Mobius inversion formula saying that we could solve the formula for F of N. All right, the converse of Mobius inversion formula is also true. So let me write it down. In other words, this is an F and only F theorem. So the converse is going to go like this. So this is converse of Mobius inversion formula. And the inverse reads like this. If we have, again, F and capital F are number perfect functions, if F of N is D divides N of mu of D, F N over D. All right, and this is also the same as actually D divides N, M of N over D, F of D. So these are true for every N being a positive integer. Then we can solve for capital F, and F of N is D divides N of little f of d. All right, remember the other statement goes in there. If this one is true, then this one is true. So this one goes the other way around. The proof of this is actually very, very similar to the proof of the previous theorem. All right, and it goes like this. Let's actually go with f of n. This is equal d divides n of f of d. And I'm going to substitute for f of d from this f of n. And I want to use actually the, the second version of this. So this one is equal to summation d divides n. And then I want to go with, we need a different divisor in here. We use k divides d. So I'm going to substituting actually for f of d. And then this becomes mu n over k. And then this is f of k. All right, let's see in here. Actually, I want to use in here d, not n, because I'm using f of d. All right. Now, let's work on this a little bit, okay? Let me actually use a different notation. Let me use the same notation as I did. Let me use C in here. So I have C. C and C and C. All right. Now I claim that we could write this last formula in a different form. So I'm going to say that this one is actually equal to summation C divides N, capital F of C, and summation D, which I'm going to write as Cm, all right, divides N of mu D over C. Okay, let's actually justify these in here. So let's look at this. Now remember here we have D divides N and D divides N and also C divides D. So I want to put these in a reverse order. We have C divides D and D divides N. Both of these implies that C divides N. And the second summation in here, first we have actually C divides D. So let me write this one. C divides D implies I could write C as Cm, all right, for some integer m. And then also this divides, of course, n, okay, because D divides actually n. So that's why we could actually switch these, all right? And then we could write this is equal to summation as C divides N of F of C. And then we have the summation of M divides from this here. I want to write it as actually M divides N over C. All right. So I want to divide that as this. So we can say this is N over C. And then we can have this is mu of m. Actually, mu of m. All right, because it is d. All right, so if I substitute by Cm for this divided by C, this is end up with that. The reason we want this is we want to actually use this idea about the summation of the values of Mobius function. All right, this is again equal to 1 if n over C is equal 1 and 0 if n over C is bigger now. So once again, we end up with only one value. This means n is equal to C. All right, from this sum, we only end up with the f when C is equal to n. So this becomes f of n. And of course, we have 1 only when n is equal to C. And this is exactly actually what we wanted to say. All right. Now we could actually restate the Mobius inversion formula as an if and only if. So let me just put it in one place. So here is the theorem, which we call the Mobius inversion formula. And it reads like this, again, if f and little f and capital F are number theoretic functions, with domain Z plus. Remember that arithmetic function could have their domain all integers, but because we are using Mobius function, it's only defined for positive, okay, integers. Then we actually say that f of n is equal d divides n of d if and only f we have the f of n d divides n of mu of d f n over d, or you can write this one the other way around, d divides n and mu of n over d f over d. Again, the reason for these being equal to each other, because as d runs through divisors of n, n over d runs through the same divisors in a reverse order. All right. All right. Next, we're going to look at some applications of Mobius inversion formula to derive some identities concerning number theoretic functions. And identities that we're going to derive here would be very hard to derive without using the Mobius inversion formula. And this is actually one of the advantages of this idea. And later on, we're going to see more of these types of identities when we discuss Euler's phi function. All right, so here it is, applications of Mobius inversion formula to derive number theoretic identities. Let's just start with the number of divisors. You remember that tau n is equal to d divides n 1. So in other words, tau of n, it has the same form as that capital F of n, which is like this. Okay, so in this case, the F of n is equal 1. That's the identity. So with this, then we can write the 1, which is the F of n, all right, as sum d divides n of the mu of d, and then tau of n over d. Of course, you can be also written the other way around. D divides n of mu n over d. And you can check this, actually, if this is true or not. I mean, evaluating, taking a certain value and compare the two sides. All right, another one has to do with sigma, the sum of divisors. Remember, we wrote this one as d divides n of d. So the function that we are summing in here, the f of n in this case, is equal to n. All right, now when we solve for this f of n, in other words, I could write this one as d divides n f of d, where, of course, f of n is equal to n. All right, so now by Mobius Inversion Formula, this tells us that the f of n, which is equal n, is summation d divides n of mu of d sigma n over d. So in other words, this gives us a partitioning, all right, of n. We write n as a sum in terms of the sum of divisors function and Mobius function. And as I say later on, we're going to be looking at more examples with useful identities. All right, one other thing. Remember also in section 6.1, we mentioned that if we have the function small f of n is multiplicative, then the sum, which is the capital F of n, which is defined, it's called sometimes called symmetry, all right, of f, all right. So record this in section 6.1. We have this result. If f is multiplicative, then f of n, d divides n, d is also multiplicative. Now, with the Mobius inversion formula, you might ask that question. Yes. Is it true? If f of n is multiplicative, then little f of n is multiplicative. And the answer is yes. And now, with the help of Mobius inversion formula, actually, we can prove this. So we're going to state this is formally in the form of a theorem and prove it. So here's the theorem. And this is theorem 6.8, and it says that with F and capital F, the number theoretic function such that F of n is defined this way, then if capital F is multiplicative, then little f is multiplicative. The proof is very simple again. We're going to let m and n be relatively prime integers. And we're going to look at this. Now, by Mobius Inversion Formula, because it doesn't require anything to do with multiplicative, okay, in the formula itself. Mobius formula. We have f of n is going to be d divides n, u of d, and then f n over d. Well, let's take the value of this function at mn, okay? So we're going to take f mn equals d divides mn of u of d in f mn over d. Now, we need to recall actually a property for divisors of two relatively prime numbers, all right, which is this. D divides mn if and only if D is equal a product of two divisors, D1 and D2, where D1 divides m and D2 divides n. And moreover, we have the greatest common divisor of D1 and D2 is equal to 1. In other words, the set of divisors of mn is nothing but the all possible divisors of m and n multiplied together. Now with this, then we can write this one here, f of mn, as instead of using d, we use d1, d2, divisor of mn, of mu d1, d2, then f mn over d1, d2. And since d1 and d2 are relatively prime as well as m and n, we can write this together with the fact that mu, all right, is multiplicative and the capital F is also multiplicative. So we keep the summation in here as 1, and then we're going to separate this. So this one is mu of d1 because this is multiplicative, and mu of d2. Also the f, we can write it as m over d1. Remember, this is actually an integer, and f n over d. Again, the reason for this is mu and capital F are multiplicative. Now, these quantities are independent of each other, so I can write them using two summation notation. D1 divides M, and pull out the D1 terms, and then summation of D2 divides N, and mu D2, and then F, N over D2. The first sum is nothing but little f of M, and the second is f of M. So this means that the function f is actually multiplicative. All right, I think this is it for this section. So I'm going to stop right